Okay, welcome to lecture 4.2. Okay, I want to explain what a Logit um, estimation technique is. It's the exact same as a Probit. The only difference is that we have a different assumption about the distribution of our random variable. In fact, let me go back to the. So this was our Probit. All I'm going to do now, I'm going to have the exact same setup. Okay, there's an underlying latent variable. I said last time I said it was C. Now let's just go back to 0. Okay, so we're going to have with the Logit estimation technique, the dependent variable is 0, 1, just like Probit. We're going to talk about an underlying latent variable, just like a Probit, that's going to be equal to that underlying latent variable is going to go from negative infinity to infinity. If it's above 0, we say the dependent variable is 1. Below 0, it's the dependent variable is 0. Okay, just like a Probit. Everything is just like a Probit. That whole setup, and I'm going to keep the same set of independent variables. All I'm going to change is I'm going to make that epsilon t have a different distribution. Okay. Before I do that, let me explain what a logistic distribution looks like. So, if epsilon t, so if that's epsilon t is our random variable, if epsilon t is distributed standard logistic, then the probability epsilon t is less than or equal to z, okay, where z is just some generic value, okay, the probability that random variable is less than z just equals this, e to the z divided by 1 plus e to the z. That is the c.d.f, the cumulative distribution function of a standard logistic random variable. Okay, so now that's it. That's okay. If that is a logistic distribution, now remember before, if epsilon t was normal, we would say the probability epsilon t is less than z is this function, this very complicated function, negative 0 to z 1 over 2 pi e to the negative z e to the negative u squared divided by 2 du. Okay, so with a logistic, we have kind of a simple formula to describe the c.d.f of the random variable. If it's normal, we have a kind of complicated formula. In fact, we can't actually have a closed solution to say what that equals. We have to keep it in this integral form unless we use our tables and look it up. We just call it phi z and start looking up the different values of it. Okay, now that's the reason a lot of people use Logit rather than Probit. It's just because Logit's a simpler formula. The logistic distribution is simpler than the normal distribution. And in fact, in the old days, say the 70s, when the computer speeds were so slow, you had to estimate that value, phi of z, you had to do it numerically. You had to set up a routine in a computer, and you said, let u go from, it's supposed to go from negative infinity to z. And it turns out, if you look up in these tables, when u is less than 4, that value is tiny. So what you would do in practice is you would say, well, you're supposed to go from negative infinity to z. For all intents and purposes, if you go from negative 5 to whatever z is, negative 5 is close enough to negative infinity, because that value, when u is evaluated at -5 is very, 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 very close to 0. So that's what you do. You set up your computer to say integrate this value as u goes from -5 to z might be 2.4, whatever it is, and then you actually can't integrate it. What you have to do instead is do this approximation to the integral. So you have to set this up where your d value, you do this in steps. So you take u equals -5 and then try it again at -4.9. You estimate the you estimate the new value, -4. You say, what's the average of those two when u is at -4.95? Okay, I'm going over this fast. And then you multiply that by 0.01. You have that step value where u increases in steps of 0.1. Did I say 0.01? 0.1. Now, if you want to make it even better approximation, you let u go from -5, and next try it at say you want to make the steps 0.01. So you go -5, try it again at -4.99, try it again at -4.98. Evaluate this at all those different values of u, multiply it by whatever the value of your step is, and that's what you do to approximate that integral, okay? But the whole point of this is that in the old days, you had to set up a computer to approximate that integral, and it was a mess. So every time you evaluated that, you had to do a lot of steps to calculate it. So if I said, make your step value 0.01 and that z is 2.4, what's the number of steps? Well, you go from -5 to 2.4, but that's at 7 times the step interval is 0.01, so that's about 700 steps every time you calculate that value. And in the old days, when computing speeds were slow, it took a really, really long time to calculate that. And then you didn't have the exact value. You're only getting an approximation. Okay. In the old days, what we do is say, well, this logistic function, the c.d.f, or you could take the derivative of that to get the PDF of a logistic function. It's going to look a lot like a normal. You graph it out, they look very similar. So you say, that's a very good approximation to this. Let's use that instead, because the computing speeds are going to be better. Now, where computing speeds are so fast, we don't have to worry about those problems. You say, well, you might, and we have theoretical reasons to believe error terms are distributed normal rather than logistic. We have the Central Limit Theorem that says that, if that error term is the sum of a whole bunch of random variables, and that error term represents the sum of these things, because of the Central Limit Theorem, it makes sense to assume that epsilon is distributed normal. Okay, we have good theoretical reasons to believe that. Okay, so in the old days, we'd say, even though we believe epsilon is really distributed normal, we don't have the computing power to estimate things correctly and quickly if we assume the proper assumption. So instead, we're going to make this approximation that it's logistic. Okay. Now, the final point. Let's go back to the 70s when people did, even now, I don't think anyone would care if you say, assume your error term's logistic rather than the normal. Big deal. Okay. If instead we assume that this error term is distributed standard logistic, this is the c.d.f of that. E to the z rather than phi of z. Okay. Let's see what happens when we make that assumption. And instead we make that assumption. So here's what I'm going to do. Okay. Epsilon t instead now is standard logistic. You know, I don't think it's actually, you know, I don't think logistic is actually quite symmetric. It comes close to being symmetric. You know what? Instead, what I'm going to have to do, I can't do that trick to say we can flip it. So what I'm going to do is I'm going to assume that negative epsilon t is distributed standard logistic. Okay. So the distribution, you graph it out, it almost looks symmetric, but it won't quite be. Okay, so I'm going to erase this. This was all for the normal case. Okay. I'm going to flip it. I'm going to make, instead of C, I'm going to make it 0. Okay. So here's what we have. So logistic, it looks just like the Probit. Okay. We have this latent variable. Logit, just like a Probit, the dependent variable is 0, 1. Okay. So we want the probability that that latent variable is greater than 0. So we rewrite, we substitute in for yt star, substitute, make 0, set it back equal to 0 instead of c. Here's what we get. Okay. Instead, we said the probability that epsilon t is less than that equals phi of that. You know, I'm going to keep the phi for just a second. Instead, I'm going to substitute what it equals when instead we assume that that epsilon t, I'll use red. Instead, we're going to assume that epsilon t is standard logistic. All we do is we substitute e to the z, okay? Where now z is, by the way, and c is 0, okay? Z is just beta 0 plus beta 1 times xt. So that probability function just equals e to the beta 0 plus beta 1 xt divided by 1 plus e to the beta 0 plus beta 1 xt. Okay, that's the probability term. Okay, so now the final step, I said, where we're going to write the likelihood function. And remember, our dependent variables, y1 equals 1, y2 equals 0, y3 equals 1. Our L for the logistic is just going to equal this term, where instead of xt, we're going to substitute x1. So we get e to the beta 0 plus beta 1 x1, all divided by e to the, 1 plus e to the beta 0 plus beta 1 x1 times 1 minus, okay, let's go y2, the dependent variable 0, so we get 1 minus that probability, and where instead we're going to substitute, instead of x1, x2, because it's observation 2, e to the beta 0 plus beta 1 x2, all divided by 1 plus e to the beta 0 plus beta, there's a beta 1 x2, times our likelihood for the third observation. So the probability y3 equals 1, that's just going to equal e to the beta 0 plus beta 1 x3, all divided by 1 plus e to the beta 0 plus beta 1 x3. Okay, so that's it. So in red is the logistic, that's the logit that's the likelihood function when we use the Logit technique. The old board, which I just erased, where instead we assume that epsilon t is normal, that's the likelihood function for the Probit technique. Okay, so you've seen both now. Okay, now here's what I want you to remember. Okay, here's where we're going. Now I'm going to start talking about the McFadden paper in a second. In the McFadden paper, he makes a similar assumption about epsilon t. Instead, he's going to assume that that epsilon t is distributed Weibel instead of standard logistic. Okay, when you do that, okay, this is like kind of a magic trick that I'm not sure if McFadden was the first. He might have been, but once you do that, you get your likelihood function starts having these terms, this e to the stuff, divided by other e to the stuff terms. Okay, now in a standard logistic setup, your dependent variable is 0 or 1. Okay, in the McFadden paper, McFadden's going to consider where your dependent variable can take something like 6 different values. Okay, it's going to be the choice of transportation. So it's going to be you choose your car, you choose BART, you choose bicycle, you choose walk, you choose cab. So I think what I named like 5 or 6 right there. So there's 5 or 6 choices. If instead McFadden had just said, assume there's only 2 choices, BART or car, then he could have set that up as a Probit. Okay, the dependent variable is a binary case. But this was the 70s where the Probit likelihood functions were just such a mess to program, and it took a long time for the computer to program. So he probably would have set it up as just a logistic case. And it turns out when he has that what he sets up, the special case, he has a more general estimation technique where there's 6 forms of travel. If instead he had limited it to 2, he would have gotten the exact same likelihood function as a Logit. Okay, so note that once we get his likelihood function, it's going to kind of look like the logistic, the Logit likelihood function. Okay, keep that in mind. Okay, so that's next. So that was finish 4.2. Okay, I will see you in 4.3, where I'm going to discuss the McFadden setup. Okay, see you there.